We're in the middle of several lessons where we're learning about evolution, learning about the evidences for evolution. One of these evidences is something called biogeography. Biogeography are the global patterns of species distribution, which can be used to explain evolutionary relationships. These patterns can be found in the fossil record. When we study the distribution of fossils, we see a pretty extraordinary thing. There are specific fossils within geological layers that are found on many different continents. How is this possible? Does this mean that members of these species were able to travel over these large distances, perhaps even traveling between disconnected landmasses? Or perhaps the oceans were not there? There's another explanation, and you are probably familiar with it. Perhaps you've heard of Pangaea. It was a supercontinent that existed hundreds of millions of years ago, and is one of the several supercontinents that have existed throughout Earth's history. It would make sense that fossil deposits are now on different continents because this land used to be connected. But how did we go from a supercontinent to many continents? In 1912, Alfred Wegener proposed that the continents were somehow drifting around the surface of the Earth. But the mechanism was unknown. Was it due to seafloor spreading? Was it due to centrifugal forces due to the rotation of the Earth? During World War II, there was extensive mapping of the ocean floor. One person who was involved in the mapping project was a geologist by the name of Marie Tharp. She was a graduate of Ohio University in Athens. Her work, for which was largely uncredited at the time, helped to produce the very complete mapping of the world's ocean's floor. It was at that point when scientists realized that the seafloor was not barren, plain, nondescript, but actually was a very dynamic place. Here's some additional observations that have been made. Seafloor sediment, the stuff that settles down through the water over time, gets thicker further away from the ridges, as if that ocean crust has been around longer. At the ridges themselves, the crust itself is thinner and has been dated to be younger rock through radiometric dating. And finally, there's definitely more earthquakes and more heat transfer from the interior at these ridges. From this, it's been concluded that an ocean ridge is a place where ocean crust is forming. The ocean floor actually increases in area. There are other locations, ocean trenches, where the ocean crust is disappearing, dropping down below other crust. To understand this, we need to have a clear picture of the structure of the Earth. You're probably familiar with the fact that the Earth has layers. There are actually two ways we can divide the Earth up into layers. The first is by classifying the layers by composition. In other words, what's the predominant materials found? There are three compositional layers of the Earth. There's the crust, which is the outer rocky layer. There are two types of crust. There's the continental crust and the oceanic crust. Continental crust, the stuff that you walk around on, is older and thicker and is made of less dense rock, mostly granite. Oceanic crust has been dated to be younger. It's also known to be thinner. It is made of more dense material, mostly basalts. Below the crust we have something called the mantle. This is largely made up of silicate rocks, so it's a different composition than the crust. It's also denser than the crust. And finally, we have the core, which is mostly made up of iron and nickel metal and has the greatest density. The second way to identify layers is by how the material behaves. We call these mechanical layers. This would include things such as, is the material a solid or a liquid? Is it rigid or can it flow? There are 5 mechanical layers. There's the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core. Just as a point of interest, you notice that the outer core is liquid. The flowing moving metal is what produces Earth's magnetic field and shields us from high-energy solar wind. We cannot survive without it. The only 2 layers that we need to focus on and understand for plate tectonics are the top 2 layers. The lithosphere is a solid. It includes the crust in the very top of the mantle, those compositional layers. This is what is broken into pieces that we refer to as tectonic plates. Below the lithosphere is something called the asthenosphere. It's mechanically different in how it behaves. It's more viscous. It's able to flow. We refer to this as being plastic. This is found in the upper mantle, and we would say it flows not like water flows, but like tar flows, or like asphalt on a road would flow. It has the ability to change shape, to be flexible, to be malleable. The diagram here shows how plate tectonics works. Convection currents exist within the asthenosphere, the slow-flowing upper portion of the mantle. Hot rock material rises because it is less dense. As it reaches the lithosphere, it begins to move horizontally, cools, and then begins to sink back down into the mantle. This horizontal movement of the asthenosphere moves the lithosphere plates above. Where plates move apart at ridges, new crust is formed by the rising magma. Where plates come together, the more dense lithosphere of the oceanic crust is driven down below the less dense continental crust. This figure shows the different plates into which the lithosphere is broken. Larger sections are known as the major plates. The small ones are known as minor plates. You'll notice arrows on this diagram that indicate the direction plates are moving. In some places, the plates are moving away from each other. These plate boundaries are known as divergent boundaries. The example here on the right is showing the mid-Atlantic ridge. Rising magma at this point creates new oceanic crust, and we see something called seafloor spreading. Currently, the Atlantic Ocean is getting wider. In other places, we see the plates moving towards each other. These are convergent plate boundaries. Here, oceanic crust would dive under the continental crust. In other places, we see boundaries where the plates are moving parallel to each other. These are called transform plate boundaries. A great example of this is the San Andreas Fault found in California. The convection currents in the mantle can change. Upwelling can begin in places that did not exist before. If this occurs in the middle of a continent, the continental crust can begin to pull apart as a divergent boundary forms. This is occurring in Africa and is forming the Great Rift Valley. The map in the lower left is a prediction of how a new ocean could form as this continent splits. Let's review some of the parts of the theory of plate tectonics. The Earth's outer layer is a solid, rigid shell, which we call the lithosphere. And this lithosphere is divided up into several plates. These plates glide over a more pliable, less rigid layer called the asthenosphere. Convection currents, the rise and descent of different density materials beneath the plates, is what drives the plate motion. Oceanic crust is formed at oceanic ridges, the divergent boundaries, as the magma reaches the surface and cools. And in other places, the oceanic crust is subducted and recycled back at convergent boundaries. The changing size of the oceanic crust constantly shifts the positions of the continental crust, resulting in something we call continental drift. This figure shows how our current continents would fit together to form the last supercontinent, Pangaea. It existed from about 335 million years ago to 175 million years ago. As mentioned before, plates move together at convergent plate boundaries. Back when this continent formed, plate boundaries containing continental crust moved toward each other. At such a convergent boundary, neither piece of crust was able to move down under the other. Instead, mountain ranges are formed. Perhaps you have driven through the Appalachian Mountains. You may even have thought that they really didn't look like mountains at all, at least not like the Rockies, the Alps, or the Himalayan mountains. This is because they're really old and have worn down due to erosion. At one point, they did look like the Alps. Can you imagine the skiing? The Himalayan mountains are forming today and are still growing. This is because the Indian plate is slamming into the Eurasian plate. Both are moving north, but look for the Indian plate to be cited for not maintaining a safe traveling distance. As a result, the Himalayan mountains are growing currently at a rate of approximately 6 centimeters per year. And so in conclusion, let's review the evidence for plate tectonics. Oceanic crust is much younger than continental crust, showing that it is constantly being formed at mid-ocean ridges and destroyed at subduction zones or trenches. Seismic activity occurs along plate boundaries, which shows that these plates are constantly moving relative to each other. The collision of plates has caused the formation of mountains. And we can see that the shapes of the continents, if we look at the globe today, appear to fit together like puzzle pieces, indicating that at one point they were connected in supercontinents. And finally, fossil remains stretch across continents, indicating that at one point they were together. We'll look more at biogeography in our next lesson.